4.1, day 3, talking about applications of exponential functions. And you are going to need your calculator for these, so keep that TI handy. So let's just start off with an example. We're actually jumping to a word problem here. So an investment increases by 10% per year. And this happens for 4 years. And if you ever find one of these, let me know, because that's a pretty good interest rate. So you got an investment that increases 10% per year over 4 years. So I want to know what the total percent increase is. So by what total percent does it increase? And I'll give you a hint, the answer is not 40%. Well, that might be seem like the thing that pops in your head first. It's not 40%. Okay, so let's think about just the first year. So year 1, well, it's going to go up by 10%. That's our R value. So that's our rate. It's going to grow 10%. So our growth factor, our multiplier, B, would be 10% more than 100%. So you could do 1 plus 0.1. So 1.10. That would be our growth factor. If you just want to write 1.1, that's okay too. So year 1, it's going to go up 10%, so I don't even know what the investment is. It doesn't really matter. We don't need it to answer this question. So year 1, the investment is going to get multiplied by our growth factor. So it's going to be multiplied by 1.10. That would increase it by 10%. It's like 110% of your investment. So that's a good thing. That's year 1. Okay, and then year 2, it's going to take that amount and multiply it by 1.10 again. So year 2, we had the same investment that we had started with, times 1.10. And then this amount, whatever this is, that gets multiplied by 1.10 again. Okay, year 3. Again, I don't know what the investment is, but I know that whatever I started with, and then what I had in year 2, and notice I'm color coding these. Year 3 gets its own color, so I'm going to take that and multiply by 1.10 as well. Okay, hopefully you see where I'm going with this. Year 4, same concept. We're building up each year, multiplying it by 1.10%. So investment from the first year got multiplied by 1.10, and then the second year, and then in the third year, and then now finally in the fourth year. Okay, so this is really all we need to answer the question. So 1.10, let's combine like terms here. That happened 4 times. So really we just had our investment multiplied by 1.10 to the 4th power. And that is a number you can calculate easily just using your calculator. 1.10 to the 4th. So our investment at the end of the day would be multiplied by 1.4641. So that should give you a clue as to why it's not 40% already. It's a little bit more than 40%. So let's answer the question, what was the total percent increase on this investment? Well, let's compare it to 1. So the total increase, if you compare it to 1, what's left over? 0.4641. In other words, 46.41% was our total increase. So we were able to come up with that without knowing the actual investment. We just knew what the interest rate was and could operate without any other numbers. I really like these kinds of examples because it illustrates what exponential functions do. Right? And I know we have the compressed version here, but this really illustrates it. Okay, let's look at example 2. Example 2, another real-life scenario. So the population of a country in 2005 was 53.4 million. And it's growing at a rate of 2.3% per year. So it's growing pretty quick. Here's my little picture of a country. Bonus if you can actually tell me what country that's trying to represent there. So I want to know, can you write this equation? Can you write the exponential function? In the directions, like what you'll see on the test and the homework, can you express the population, P, which is in millions, as a function of time, T, which is the number of years since '05? So it's a little bit wordy, but it should be pretty straightforward actually. So we need to identify what these numbers represent. For starters, 53.4 million, that's our A value, right? That's our starting value. That one's easy to point out. And then 2.3%, if it's growing at 2.3%, that means our R is positive 0.023 as a decimal. So that's our growth rate. So in our growth factor that we're going to multiply by, our B value, well, that's 1 plus R. So 1.023. That's what we're going to multiply by every year. So once we know that, we can throw this right into the equation. Just make sure you use the correct variables. So it's asked for P and T. And a lot of these will ask for T. Exponential equations use time. So P, that's our output, the population, starts at 53.4. And then the multiplier we said was going to be our growth factor of 1.023. And then we raise it to the exponent of T. And T is the number of years since 2005. Okay, so I'm good with that. That's good. But then part B, there's always a part B. Predict the population for this country. Predict the population in 2015. And this may seem like an easy question, a simple question, but I'll tell you a really common mistake that kids make is they take 2015 and they throw it in there for T, and they get a big number and they think it's all good. They get like 1 billion for the population, right? But that would be incorrect. So 2015, that's 10 years later, right? That's 10 years after 2005. So really, the T value that you should plug in, that's just T equal to 10. So if you can identify that correctly, you're in business. Plug in 10 for T, and then we can calculate. So put the 10 here for T. That one you can do easily in your calculator. Make sure you have a multiplication sign here, or parentheses. It's about 67.034. And now we need to be particular about the units we're in. So since we left this as 53.4, we didn't put all the zeros out. This is in millions, right? 67.034 million people would be the population. So if you can set up the equation, you're halfway home. Identify what values go in for which variable, for A and B, and then just make sure you don't get caught up trying to put the year in. It'll probably overflow your calculator. Make sure you put the years after 2010. So T is 10. All right, one more example for these notes. Example 3. We got a car that's purchased in '08 for $21,500. And it's depreciating, as cars do, at a rate of 15% per year. And since I'm kind of partial to the Honda Accord, I'm going to put that in there too. I think they're great, dependable cars, so I don't think it would depreciate that much, but I'm going to put the Accord with this one. Okay, so again, I'm going to ask you to come up with the model. So can you express the price, P, as a function of time, T, and that's going to be the number of years since it was purchased in 2008. So let's just identify the values and put them in the equation correctly. So 21,000 up there, that's going to be our A value. That's the starting value for the car. It only goes down from there. And then our rate. So it's actually depreciating 15%. So that means R has got to be negative 0.15. So it's actually decaying. So our B value, if I compare that to 1, So 1 and negative 0.15. So my multiplier is just going to be 0.85. So anything less than 1 for the multiplier is going to be exponential decay, which is what we have in this case. Okay, so now the equation should be simple. Now we've got these identified. So we've got P equals the starting amount, 21,500, and make sure you put the right value in here. This is 0.85. So we're multiplying by 0.85 to the T. So I know it's decreasing, and this is the other most common mistake I see. I know it's decreasing by 15% a year. That's totally true. So what are you multiplying it by to make it do that? Well, if you compare it to 100%, now you're down to 85, so you're multiplying by 0.85. Okay, part B. Let's predict the car's value in 2016. And again, don't plug in 2016. Be aware of the situation. That's exactly 8 years after 2008. So make sure you plug in T equals 8, and we'll be all good. So take my equation and plug in 8 for the T. And then that's pretty easy in the calculator. I round it to 2 decimal places, so approximately $5,858.55. I thought my Honda quarter throat would hold better value than that. Okay, part C. This is a new type of question. In what year will it actually be worth less than $1,000? So in what year will the car be worth less than $1,000? So far I've just made predictions by plugging in a year and you tell me the price in that year. But now I want to know, here's a price, $1,000. What year will it actually reach that or be less than that? So algebraically we don't have the tools to do this yet, but we can do this in our calculator. So let's graph this function in our calculator, and then let's look at the table. So I'm going to enter the function into y1, this function. I'm going to have to use x's and y's, but that's okay. I'm going to enter the function into y1, and then I want you to look at the table. Look at the table of values. If you don't know what I mean by table, just hit second graph. That's the table. Alright, so let's get those calculators out. I'm going to go to y equals, whoops, not that button. I'm going to hit y equals. Then I'm going to type this line in, or this function in, $21,500, 0.85 to the x. Okay? And you can look at the graph right now, but it really won't make a difference because we're not going to use the graph yet. I just want to go to second graph, and that's actually where the table's at. So if you look at these values, at 0, it's at 21,500. That should make sense to you. That's our starting value. And if we scroll down by the year, so there's year 8, by the way. We already calculated that one. When does it become less than $1,000? Keep going. Aha. Looks like the 19th year. So here's all my values. When does it break 1,000? Right there. The 19th year after 2008. So that's how we can answer this question. Enter the function and look at the table. Like if you're going to graph it, we didn't look at the graph yet, but you can look at the table of values. This is actually year 2027. Chords really hold their value, I'm telling you. Okay, so using the table gives us a method. It's actually a little bit of approximation. But we did get the year 2027. That's the right answer. If you want to know the exact time, like the exact point, like a decimal for the year, well, graphically we can look at it. If we just graph in y2, graph the function y equals 1,000. So that's going to be a horizontal line. So if we graph the y values equal to 1,000, graph that in y2, because this one's already graphed in y1. And then all you have to do is look at where they intersect. So find the intersection. And if you don't remember how to do that, that's okay. I'll tell you. you just hit second, trace, that's where most of your commands are, and then select intersect. So that's if we want to get an exact value as opposed to getting an approximation from the table. Let's take a look at that. Alright, so I'm back my y equals screen here to plot some lines. I've already got my function plotted in y1. Now in y2, I'm just going to write 1,000. That's going to give me a horizontal line at 1,000. And just to make sure we can see everything, let's make sure our window is reasonable. So right now my window, my x min and max, -10 to 25, that seems reasonable for the years. The y max, 15,000, the y min 0, that's also reasonable. In fact, the y max doesn't even need to be that high. That can be, let's say, 10,000. And let's take a look at the graph. So the point of adjusting the window is as long as you can see where these two graphs intersect, then your calculator will give it to you. So that's my intersection point. I hit second, trace, intersect. That's the fifth one. First curve, yes. Second curve, yes. So just hit enter twice. Guess, hit enter one more time because it's selected both curves now. It's going to tell you right where they intersect. So for $1,000, that's 18.878 years since 2008. So a rough approximation still will be okay. We'll say about 19 years. So this method with the intersection, that's if you want to get a precise value graphically. In either case here, it'd be okay to just use the table because 2027 is the reasonable answer. So the year 2027, the chords hold their value forever. In conclusion, what do we do with these? We took the word problem, identified the values that we needed, set up the equation, then we made predictions, and we can even make predictions about the output. We can actually calculate when it will reach these output values if we use the graph on our calculator. That's all for these notes. I'll see you in class.